Today we're going to talk about polarity and intermolecular forces, the attraction between molecules. So polar bonds. You guys ever heard of polarity? Polar opposites, right? We might have someone that is, what do you call that? Bipolar, right? Okay. Well, what is that? What is bipolar? Yeah.
Having two extremes.
Yeah, they're just either here or over here, right? Okay. And that's what we're talking about when we deal with polarity. So polar bond is a covalent bond. That means what happens to the electrons? They share, good. Where the electrons are shared unequally. Now, what would cause them to be shared unequally? The atoms that are sharing, one of them wants them more than the other. Which one?
The one with the negative charge. The one that has
More
more electronegativity.
electronegativity, right? So if it has more charge, then we're talking about ionic compounds, right? Where it's one positive. So it's not charge, it's which one has a higher electronegativity value. Do you remember that trend? And you also get that electronegativity chart on your reference sheet for the exam, right? So you can just look at those. Whatever one has the highest number has more electronegativity, has more electrons. So it's taking more of those electrons to itself. Good? All right, to determine if a bond is polar, we're going to follow a few steps. Step one, we want to determine the electronegativity value. And so you have this chart on every exam, so you just look at it. So determine electronegativity value for each element. So we're not talking about the whole compound yet. We're just talking about a single bond. Okay? So there's going to be two atoms. So we want to find the electronegativity value for each one of those atoms in that bond. Good? Step two, we want to determine the difference in electronegativity. Negativity. Is that how you spell it? Negativity. So in other words, we'll just say delta E for difference in electronegativity. Did we talk about difference in this class? The triangle symbol? Okay. So that means a change in. How do you find a change in? You find the value of the final minus the value of the initial. In this case, it doesn't matter which one's final, which one's initial, because there's just two of them, right? So for this, we could just say E1 minus E2, and it's the absolute value. What does absolute value mean? It's always going to be positive, right? It doesn't. So we just take big number minus small number. Good enough, right? So I know that equation looks a little scary maybe, but we're just finding the difference, okay, between the two electronegativity values. And step three is if there is a difference greater than 0.4, then we're going to specify which atom is more negative and which one's more positive, okay? So if there's no difference, we just say it's nonpolar, right? They're the same. And it's a nonpolar bond. But if they are different, enough of a difference, I'll give you a chart in just a minute. So specify which atom is partially positive. Why do I say partially?
Like
Could-
for
yeah.
oxygen is partial.
Uh-huh. So like in an ionic compound, you have sodium and chlorine, for example. One's positive one, one's negative one. They're not partial, they have a full charge, okay? For covalent compounds, they're not charged. Why do we call them partially positive, partially negative? Because the electrons tend to go toward the which one? Partial positive or partial negative?
Partial positive.
Is that, what do you, everybody think?
Positive, because they're negative.
Attractively positive.
If it has more, so this is not an ionic compound. If it has more electrons to it, is it going to be more negative or more positive?
More negative.
More negative. More electrons, more negative. You with me? So it's not an ionic compound, and that's the difference. So we say that's partially negative. The one that's more electronegative is partially negative. The ones that less electronegative is partial positive. Yeah, question.
If it takes more electrons, negative,
Uh-huh.
the atom doesn't matter.
It's not negative, but it's partially negative.
Partial.
So it kind of, if it was an object like this pencil, one side might have more electrons than the other side, right? It's still neutral together because it's all together. But, so partially positive, I'm gonna give it delta plus. That's what we use in chemistry. It's just a Greek letter, okay? Specify which atom is partially positive and partially negative. And that's delta minus.
Wasn't the triangle delta?
Yeah.
And that's delta?
Yeah, so that triangle's a capital delta. Good, why?
Is it like a squiggly D or an S?
It's like a squiggly D.
Okay.
It looks, yeah, it's not a perfect drawing, but
I just,
yeah.
Do we have to use the, or can we just use the triangle one?
If anybody else looks at it, they'll say, what is that? Right? This is what everybody uses in chemistry, is the squiggly delta. But for this class, I don't care what you use, right? You could, if you want, you could just say plus and minus. Just know it's not a full positive charge, it's not a full negative charge. Got it? So it really doesn't matter. Okay, this is just part of the process. Okay? So let's do, well, before I give you an example, I'm going to give you the chart to determine whether something's polar or nonpolar. And you don't have this chart on the reference sheet, so you're going to have it up here or on your little card or wherever, right? So this chart is a difference in electronegativity values. So this is 0. We have one at 0.5 and one at 1.9. And these numbers are not set in stone, okay? This is just a general trend type deal. And I'll kind of give you an idea of how you know if it's close, okay? So if the difference in electronegativity is between 0 and 0.5, you guys get the notation of the square brackets and the round brackets? If it's the square, it includes that. If it's the rounded, it doesn't include that, right? Okay, just a math notation. All right, so if it's between 0 and 0.5 up to 0.5, we'll just say it's nonpolar. Meaning it's not, there is a difference in electronegativity, but not so much we don't even notice, right? Basically, it's not polar. Good? If it's 0.5 or up to 1.9, we're going to say it's polar. What do we say if it's bigger than all that junk? Ionic. Does that mean we can't have a polar covalent bond that has a greater difference than 1.9? No, it doesn't. Okay? You can. And we're not going to call it ionic. Okay? So, for example, if you look at your electronegativity chart, y'all have it with you? If we look at, let's say we have a let's say fluorine is bonded to arsenic. Fluorine has an electronegativity value of 4. Arsenic has an electronegativity value of 2. So what's the difference in electronegativity? Or 2, right? 4 minus 2 is 2. So does that mean it's an ionic compound? What do you think? Is arsenic and fluorine would make an ionic bond? No. It's 2 nonmetals, right? Or no metals anyway. Arsenic's a metalloid, but okay. But as far as we're concerned, this is a good enough scale. Good? Okay, let's do an example. Unless you have any questions. All right? So let's do a carbon-hydrogen bond. First step is we determine the electronegativity values. So y'all have your chart in front of you? So let's practice using the chart so you know how to do this when you're out of this class, right? What's the electronegativity value for carbon? 2.5. Again, you don't have to memorize this. It's on the chart. What about hydrogen? 2.1. So what is the difference in electronegativity here? 0.4. So is it polar or nonpolar? So do we have to worry about the partial positive, partial negatives? No, do not. So we're done. We'll just say this is nonpolar. Done. Okay, let's do another example. Any questions on that one? Okay. We have a carbon-fluorine bond, for example. Carbon, again, is 2.5. What's fluorine? 4.0. What's the difference in electronegativity? 1.5. Yeah? So what is this? Polar, nonpolar? It's a polar bond. Since it's polar, we have to specify which side is partial positive, which side is partial negative. I like to deal with the partial negative first. Which one is partial negative, carbon or fluorine? Fluorine, because more electronegative. Does that make sense in everybody's mind? Partial negative, partial positive. Why do we have to specify this if we know it's polar?
So the student should understand.
So we can determine if a molecule, a whole molecule is polar or not. So this is just one step in determining whether the whole molecule is polar or nonpolar, okay? We good there so far? Not too bad? All right, let's do one more. What about a nitrogen-oxygen bond? electronegativity value of nitrogen is 3 and oxygen is 3.5. So what's the difference? 0.5. Polar, non-polar. Barely polar, right? So what do? Find the partial negative, partial positive, because it is polar, right? So it is polar. Which one's partial negative, everybody? Oxygen. Nitrogen's partial positive. We good? Do we need to try some more, or because we have more on this worksheet that you picked up?
It means here, carbon gives more electron, that's why carbon is negative.
Carbon's oxygen, yeah.
It's more.
It doesn't. Well, if you let's see. So why is it more electronegative? That's a great question. But my understanding is, well, it has more what? More valence electrons. And so what would it rather do? Would it rather gain electrons or lose electrons to have the
Gain
octet?
electrons.
It'd rather gain electrons more than carbon would, right?
Yeah.
Therefore, it's more electronegative.
Any element that has more electronegative, it's gaining electron.
In an ionic compound, yes. So we're talking a little bit about ionic compounds here, but today we're talking about covalent compounds. Are you with me?
For now, yes.
Okay. All right. We ready to determine the molecule, or do we need more practice? You talk to me.
She said one more.
One more? Okay, one more. Let's do some more. So on our worksheet, so we can assign the electronegativity if you want on number 1, but that's just copy and paste, right? Let's look at section 2. So we have all of these bonds. Which one do you want to do together? Which one looks icky?
HBr.
HBr, let's do it. Okay. What's the electronegativity value for hydrogen? Do you know what chart? Do you have the chart? No. What is it? 2.1. What about bromine? 2.8. So what's the difference? Is it polar or non-polar? Polar, because it's greater than, it's 0.5 or greater, right? So we have to follow this chart, or the scale. Since it is polar, which one's partial negative? The more electronegative value. Bromine. Are we good there? All right. Now let's get to where we're trying to get to. Let's determine if a compound is polar or not. Okay? So we talked about polar opposites a little bit. What's an example of an object that has polar opposites? A magnet, right? So you have a magnet, you have a north side and a south side. They're opposites, right? So a magnet is a polar object. Good? What's another one that we use every day? Maybe every day. A battery has positive on one side, negative on the other side.
No.
Batteries are polar, okay? They're not magnetic, but they're polar. And we're dealing with this type, with charges, right? If we can separate the positives from the negatives, it's a polar molecule. You following me? So that's kind of where we're getting at. Let me give you some steps on how to determine this. So step 1 is draw the Lewis structure. Well, we'll just say, we know how to draw the Lewis structure, right? Why do we draw the Lewis structure? So that we can figure out what?
What's going on?
The molecular geometry, right? So in the end, we really need to know what is the molecular geometry. Because the Lewis structure, we can't determine if the compound is polar just by looking at the Lewis structure. And I'll give you an example in a minute. So determine molecular geometry. I'm not worried about the electron geometry, just the molecular geometry. You guys good at drawing 3D shape, 3D molecules yet? You don't have to be able to draw them. You just have to be able to see it with your eyes, not with your brain. Okay. You have to be able to see it, because if you can't draw a straight line that separates the positives from the negatives, if you can't see that, well, you can't do this. Okay. So we got to know what it looks like, and I like to be able to draw it on paper and then just draw a line. Can you draw a line that separates the positives from the negative? If you can, it's polar. If you can't, well, it's not polar. Good? All right, next is we determine if each bond is polar. Or not. And then step 3 is we perform the line test. Now, the line test, I feel like that's the easy way. We can talk about vectors. You guys ever watch Despicable Me? And the vector, the bad guy, right? What's a vector? What does he say? Does anybody remember? Has both direction and magnitude. Booyah, right? Okay. So that's what a vector is. We talk about vectors, but then we have to learn how to add vectors. I think it's a good exercise to be able to do, because this is really what determines if a compound is polar or not. And I know it's a little physics. You guys scared of a little physics? Should I just keep it simpler? Okay, I think we should do it. So I'm gonna just say here, perform the line test. All right, so let's do a little vector exercise. So forces are vectors, right? I can push with 10 pounds of force, but I also have to push it in that direction or this direction. The direction matters, right? So if I have this table, let me take this off. I hope this table slides. If I have this table and I push 10 pounds this way and someone else pushes 10 pounds this way, what happens to this table? Stays there, cancels out, right? If I push 10 pounds this way and someone else pushes 10 pounds this way, what happens to it? Moves at an angle, right? Okay. I'm going to just draw something just to help us to understand what direction it is exactly. So if I draw the length of this vector as an arrow, right? The length is how much magnitude or how much force it has in it. So if I do, let's say I'm pushing this object this way, someone else is pushing this object this way. Here's how you determine exactly what direction it goes. We draw a parallelogram. Is that a parallelogram? It's not the regular type of parallelogram that looks like that, but it's still a parallelogram, right? Opposite sides are parallel and congruent, right? That's the definition. And if we draw a line that goes from where these vectors start to the corner of this. This is the net force, you might call it, which is force 1 plus force 2. Are we getting too complicated yet? Okay. And it doesn't matter what angle. So if I push at this angle and someone pushes at this angle, can I find the net force? And just draw a parallelogram. Going to be something like that, right? Are we good? Because if we have a bond, hydrogen and chlorine, for example, this is 2.1 and this is 3.0. Which side are the electrons trying to go to? Toward the hydrogen or toward the oxygen or the chlorine? The chlorine. And so we draw a little vector here. We call this a dipole. That tells us this is a polar bond, right? But what if we have several different bonds and we got to figure out, well, do we have a net dipole or not? If we do, if we have something to where this is not zero, then it's polar, right? And if it is zero, if the net force, it all cancels out, like I push 10 pounds this way, someone else has pushed 10 pounds this way, it cancels out. It's like it's not polar, right? They're the same. It's not like a battery. Are we good? All right. So I said all that. Now let's do some examples, yeah? All right, let's do carbon dioxide, for example. What's our first step?
To find out electronegativity.
Almost. That's the bond, right? We don't even. How many bonds do we have in this compound? We have two. Do we have to memorize that? No. What do? We draw a little structure, right? So in the end, but we want to find the molecular geometry of this, right? To find the molecular geometry, do we have to draw the little structure? Yeah, that's just a step, okay? So let's draw this. We got to count valence electrons, right? How many valence electrons does carbon have?
4.
4. It has 6 total, but 4 valence electrons. You with me? Because it's on the highest energy level, it has 4. It has 2 on the first energy level, 4 on the next one, okay? Oxygen has how many? 6. There's 2 of them. We add those together and we have a total of 16. All right. Which one's the central atom? Why is carbon?
That's less.
Least electronegative. Good. So we got carbon with 2 oxygens. How many electrons have we used so far? 4. So we have 12 left. We're going to put them around oxygen, the outermost electrons. Why is the outermost? Because it's more electronegative, right? 2, 4, 6, 8, 10, 12. We used all of them. We don't have any more, so don't put any more out, right?
Only left carbon 2.
What?
Only one carbon left.
Yeah, carbon doesn't have an octet, so what do we do? What do we got to do? Move them down. Do we have to do one on each side? Or could we do 2 on one side? Two pairs. What do you think? Can I draw it like this? Everything have an octet? It does. Everything has an octet. What do you think? Should we draw it that way? No, because it's not balanced. It's not symmetrical. Symmetry is the best, right? In our purposes, it won't affect us to know if it's polar or non-polar for this case. But let's try to do it the right way. So we're going to do it to make it symmetrical, best we can. Sometimes we can't, but when we can, then do. So there's our Lewis structure. What's the molecular geometry? How many electron regions do we have? We have 2 regions. So what's the shape? Oh, it's linear. Oh, this is the shape. We're good, right? We don't have to draw anything separate. That's nice. All right. Now that we have this geometry, what's our next step to determine if this is a polar molecule or not?
Which one is polar or not?
Yeah. Check each bond. Is the carbon-oxygen bond polar? You guys tell me. Yeah. This is 2.5 and this is 3.5. Difference in 1. That's definitely polar. What direction is the pole? Toward the oxygen, right? Okay. So that means the oxygen is partially negative. All right. Now, we can draw vectors or just do a line test. What would you rather? Both, just to make sure we got it?
Yeah.
Okay. So here we have a dipole this way and a dipole this way. Which dipole is stronger, the one going to oxygen on the right or one going to oxygen on the left? They're the same. They both have a difference in electronegativity of 1.0. It's like they have the same strength. It's kind of like pushing this table, right? One's pushing this way with 10 pounds, one's pushing this way with 10 pounds. What happens? Nothing. Stays the same, right? So what do you think? Is this a polar molecule or a non-polar molecule? Non-polar. Cancels out no net dipole, right? No net force. So non-polar. All right, now let's do the line test. Some of you might like this better. Can we draw a straight line to separate all of the positives from all of the negatives in this compound? Where? If I draw it right here, do I have negatives on one side, positives on the other?
No.
No, I got negatives on both sides. Okay. What if I do it right here? Does that help?
No.
Does it matter where I draw it? Can I do it?
No.
No, it's nonpolar. If I cannot separate the positives from the negatives to make a polar object like a magnet or a battery, it's nonpolar. That's it. Okay?
And can you demonstrate why you can't again?
Why I can't separate it?
Yeah.
Because along this line, I got negatives on both sides. Along this line, negatives on both sides. Along this side, well, there's really nothing over here but a half a negative and a half a negative, a half a negative and a half a negative, half a positive and a half a positive. Right? You can't do it. You cannot separate the positives from the negatives. Is that clear? All right, let's do another one.
Another one that has that.
Let's do NH3. We've done this before. Do you want me to go through all the steps to drawing the Lewis structure and everything?
I think that would be nice.
Yeah? Okay. So how many valence electrons does nitrogen have? 5. And if you're not sure why we're doing something, you don't, how do we know that? Then say something. You are here for you, not for everybody else. So say something if you don't understand it, please. Okay?
See something.
Yeah. And hydrogen has how many valence electrons? 1. But there's 3 of them, so we're going to multiply that by 3. We get a total of 8 electrons. Which one's the central atom? Nitrogen. We have 3 hydrogens hooked to it. Does it matter where we put them? No, as long as you just put 3 sides, right? 2, 4, 6. We have 2 left. Where do they go? Around the nitrogen. Never around the hydrogen, right? Hydrogen already has an octet. All right. So now, that's the Lewis structure. Are we good at the Lewis structure? Can we just stop there and do the line test? No, we got to find the molecular geometry. What is the molecular geometry? We have how many regions? 4 regions, 1 lone pair, 3 bonded atoms. So what is the molecular geometry? Look at our chart if we have to. Trigonal planar. Tetrahedral. Oh, so the electron geometry is tetrahedral, right? But the molecular geometry, since there's that one lone pair, and if we draw it, it looks like this. Where all the H's are kind of pointing downward, and then you got the lone pair that's kind of pushing them downward, right? All right, so now we have the geometry there. We have a hydrogen-nitrogen bond. Is that a polar bond, yes or no?
Yes.
Let's see. 3 and 2.5, or sorry, 2.1. Yeah, 0.9. It's definitely polar, and the pole is going toward the nitrogen. You with me? So if we do it on the structure, for example, it would still work, but it doesn't always work. So don't do it with the structure, the Lewis structure, okay? It worked here, because these two cancel out, right? And you have one down. But the net pole, anyway, let's do it on this one here. We have one going this way, and this way. And we have none going up. So is there a net dipole? Yeah, downward-ish, right?
Is the force going from hydrogen to nitrogen, or up there you have nitrogen?
Oh, I did went the wrong way, didn't I? Sure did. Now we have an upward force. So our net force, our net dipole is up-ish, right? You with me? No, that's 3D, a little bit harder than doing, can we still use the parallelogram rule? We still can, just do two at a time, right? These two, this might be pushing this way, this might be pushing this way a little bit, pushing that way and pushing that way a little bit, right? These two cancel and we're left with two going up. Right? But we can all see that it's pushing up. Is that right? Or can you not see that? We got them all pushing up a little bit. That means if we add all those together, it's pushing the whole thing up, right? Where all the electrons are trying to go up. Good? So this is a polar molecule. Now let's do the line test, shall we? Let me redraw this because I kind of made a mess out of it. So this is partial positive, partial positive, partial positive, and partial negative. Can we draw a line that separates the negatives from the positives? Yeah, right there.
But it wouldn't work with the top one, the structural.
Not the line test, but yeah. That's why you have to know the molecular geometry. Yeah, Chad.
Question about the previous one.
CO2?
Yeah. The 4 remaining electrons on each of the oxygen, are those those are not lone pairs?
They are lone pairs, but not around the central atom, so that doesn't matter. About the-
That's why it doesn't change
Yeah.
the molecular shape, okay.
Remember the molecular geometry, we're interested in the central atom only.
The lone pairs in the same, okay.
Yep.
That's right.
Thanks for asking. Are we good with this? So who likes drawing the vectors better? Okay, good. Who likes just doing the line test? Okay. That's what I get most of, but some people just want to understand why, and that's why I teach both. Are we good?
Is this nitrogen the A? Oh, my God.
Are we good?
Yeah, I just.
Yeah, Rebecca.
If the electronegativity is polar or non-polar, like the geometry, the line test, or whatever, is gonna have the same answer, or it can be different.
It can be different. So let me make sure I'm understanding your question. If all bonds are polar, does that mean the molecule is polar?
Yes.
No. If all bonds are non-polar, do you think? Does it mean it's nonpolar? Yes. There's no force on it, right? There's no dipole. Therefore, it's a nonpolar molecule. But if they're all polar, doesn't mean it's a polar molecule. We have to check. Use the line test or use the vector test, right? Should we do an example? CCl4. If we draw this, here's the Lewis structure. And here is the molecular geometry. Is chlorine-carbon bond a polar bond or a nonpolar bond? Chlorine-carbon. 2.5 and 3. It's barely polar, right? Going this way. So that means we have partial negative, partial negative, partial negative, partial negative, partial positive. This is a polar bond, but can we draw the line? Can we draw a line separating the positives from the negatives? Where? I can't. Nowhere we can draw this. And you got to remember this is a three-dimensional object. So even though I can draw two-dimensional lines, you got to be able to just see this in your brain as well. That makes sense? But this one's pulling down, this one's pulling down, this one's pulling down, this one's pulling up. Now these are not pulling straight down. They're pulling down just a little bit. If you add all those little bits, it adds up to be this big, right? And then you have one this big pulling up. What happens? They cancel.
It's bitter to stay away.
What?
It's bitter to stay away.
Yeah. Are we good?
Yes.
So sorry,
Yeah.
what's
No, you're
the-
good.
What's the net charge or net force, I mean?
So since we can't draw a line between the positives and the negatives, it's nonpolar. Even though this is a polar, all bonds are polar, still a nonpolar molecule. And here's the key. If your molecule is 100% symmetrical, it's going to be nonpolar every time. Sorry, guys. If it's non-symmetrical, it's going to be more like this. You can draw the line test. It is polar. So here's something that might help. If your central atom has a lone pair of electrons, it's going to make it non-symmetrical. Therefore, if it has a lone pair of electrons, it's always going to be polar. Does that make sense? So if it has a lone pair on that central atom, you don't have to do all the nonsense. Just say, oh, this is polar. Because there are exceptions, yeah.
Well, just a quick question. So the force is always going toward
The more
the
electron
more
negative.
electric.
Good. So an example of CS2. What's the electronegativity difference between carbon and sulfur?
None.
Zero difference. Is it zero exactly? No, is that what it says? 2.5 and 2.5? Okay. But here's what this compound looks like. And I don't know if this is not a real compound, sorry. That's not what I was looking at. SH2, that's what I'm looking for, okay. So if we draw this, so what's the difference in sulfur and hydrogen? 0.4, right? Yeah, so it would just still say it's nonpolar, right? But here's what it looks like. We have lone pairs around there. This is still going to be a polar molecule. even though they have zero lone pairs, zero polar bonds. It's a little bit polar, but these electrons push it down and make so it's not symmetrical, making this a polar molecule. Now, I'm not going to get too much into that, but just always draw this, and always, if it has, and I haven't seen an exception to this, I'm not saying there's no exception, but if there's a lone pair on that central atom, it's a polar molecule every single time. Good? So that might save you some steps if you can recognize that it has a lone pair, right? Just draw the Lewis structure and you're done. Okay. Yeah,
I think
Salma.
I used this information, but what happened with the ionic compounds?
The what? Ionic? Ionic compounds? We don't say ionic compounds are polar. We just say they're ionic. They have positive on one side, negative on the other side. So, in a way, they are, if we did call them polar molecules, they would be more polar than polar covalent. But we just call them ionic. Make sense? Any other questions? Should we do some more? Okay. Let's do C2H6. And then CCl4. We already did that one. So let's don't do that one again. And let's do H2O.
Two of them.
What?
Two of them.
Yeah, we'll do just one at a time. All right, so if we draw the Lewis structure, we get something like that. Or should I count valence electrons? What you guys tell me what you need.
14 valence electrons.
2, 4, 6, 8, 10, 12. Does it have 14? Oh, I counted wrong. Yeah, that's not right. There we go. We good? All right, now which carbon atom are we dealing with for the central atom? It doesn't matter. Okay, it really doesn't. Now no, you're not going to be tested like that in this class. Okay. All right. So if we look at this carbon atom, for example, what's the molecular geometry? Tetrahedral. Okay. All right, let's check the bonds. We have a carbon-hydrogen bond and a carbon-carbon bond. Those are the only two bonds we have. Is the carbon-hydrogen bond polar or nonpolar? Nonpolar, right? 0.4, so it's nonpolar. What about carbon-carbon? 0, so it's nonpolar, right? 0 difference. So we have 0 polar bonds in this molecule. Well, so what do you say? Polar or nonpolar molecule? If all of them are nonpolar, it's nonpolar. We have 0 lone pairs, so it's nonpolar. Yeah, Andrew.
So earlier you said if all the bonds are nonpolar, the molecule is nonpolar.
Uh-huh.
The exception to the rule would be
If there's a lone pair. Yep.
That's just an exception.
Yep. Good. And for this class, I don't think I'm gonna even worry about that, guys. But yeah.
Can you demonstrate why it's tetrahedral?
Uh-huh. 1, 2, 3, 4 regions and 0 lone pairs. So if you look at your chart,
So you're not counting each one, you're just choosing which central atom to use.
yeah. So if I chose the other one, I'd get the same thing, right?
It's not like there's 8 or 7.
Yeah.
Okay.
Yep.
What would the molecular geometry look like?
It would look like this. So we get carbons in the center, hydrogen up here, hydrogen sticking out here. And then here we got something like this, right?
It's like 2 tetrahedrals
Yeah.
together.
Uh-huh. We good? Okay, why don't you guys try water?
It's not bad. I don't know what this has to do with chemistry.
So what do you think? Is water polar or non-polar?
Polar.
Everybody okay with that? Should we draw it anyway? Okay. So we have 2 for hydrogens plus the 6 for oxygen. That's 8 electrons, yeah? Yeah. There's the Lewis structure. Are we okay with that, or should I go a little bit slower? Talk to me. We good? All right. Yeah, Andrew.
I just always envisioned the H's as being like the
You
axis
should-
or whatever, right?
It really is.
Circle.
This is the Lewis structure. Do you see why we can't do the line test with the Lewis structure? Because if we tried doing the line test, we couldn't do it. We'd just call this nonpolar, right? Cannot go with the Lewis structure. So we count the regions. How many? 4. That means it's going to look something like this. Right?
So it's better to not.
It's bent, and this is definitely a polar bond, hydrogen and oxygen, right? So we got the partial negative for oxygen, partial positive for hydrogen, and we can do the line test. Did we have to worry about the line test? Why not? There's lone pairs around the central atom. This is definitely polar. And we all know this, right? We get electrocuted in water. Well, hopefully we don't, but we can. Water is a polar molecule. Yep. Yeah.
What would be the, molecular and electron geometry of H2O?
Molecular geometry, yeah. What is the molecular geometry? Can anybody tell me?
It's bent.
Bent.
But, you have two lone pairs, right, on
Uh-huh.
oxygen. So does that mean the electron geometry is, tetrahedral?
That's right. Yep.
Because there's four domains.
That's right.
Okay.
Yep. Electron geometry is tetrahedral. Molecular geometry is bent tetrahedral. Good? Any other questions on this? Would you like to try some more? Okay, you got a whole worksheet full of these. So on this worksheet, let's go to section 3, draws it for you. It kind of does everything except for you have to tell whether the bonds are polar and do the line test, right? And then section 4, it just gives you the chemical formula you have to determine if it is a polar or non-polar molecule.
Based on the line
Uh-huh.
from 0 to 5.
Yeah. Well, that's just the bond, and then you have to determine partial positive, partial negatives, and do a line test, right?
To get polar and non-polar.
Uh-huh. Any one of them that you want to try together? Or do you want to just try these on your own? What? CH2F2. Yeah, that's a good one. CH2F2. So let's draw the Lewis structure. We got 4 for carbon, 2 for both hydrogens, and 14 for both fluorines. I skipped some steps, but you guys follow me? Well, I didn't skip a step. I just kind of did it in my head. Are you okay with that? All right. So that's a total of 20 electrons. Okay. Which one's the central atom? Carbon. It's all lone, never hydrogen, and it's least electronegative. So it kind of covers all that. Does it matter where I put these? No, it doesn't. All right. Now, of course, it has these right here, yeah? But that's not going to really determine the molecular geometry anyway, is it? Okay. Is this a fully symmetric molecule? No, because these are different than those. If you want, we can stop right there and say this is what? A polar molecule or a nonpolar molecule? If you don't know, then don't skip the steps. If it's not symmetrical, it is polar. Yeah.
Could I put the fluorines on top and bottom and the hydrogen?
Yep. No problem. Why? Why is it no problem? Because this isn't how it looks, is it? This, if we draw the molecular geometry, we could have a fluorine up here, and a hydrogen right here, and a fluorine right there, and a hydrogen right there. What's the bond angle between this bond and that bond? The same as it is between this bond and that bond, between this bond and that bond. All about 190 degrees. That's why it doesn't matter how you draw it, or which one you put where. All right, so let's take a look at this. I don't like to draw it that way, but you can. So carbon-hydrogen bond, is that polar or non-polar? We just did it a few times.
Hydrogens.
Carbon, hydrogen bonds are
No.
nonpolar. Do we have to worry about positives and negatives?
A little
Partial
bit.
positive, partial negative? No, we don't for carbon and hydrogen because it's nonpolar. What about carbon and fluorine? Is it polar? We got 4 subtract 2.5. That's definitely polar, right? 1.5. Partial negative, partial positive. Can we separate the positives from the negatives? We sure can. We don't have to worry about the hydrogens because they're not. And can I draw this a little bit differently so we can easily see? Fluorine, fluorine, hydrogen, hydrogen. Maybe a little easier to see, right? I know that's not a straight line, but
But this is also not correct, the one you did.
what?
That's not correct. That's not correct, the one you did.
Oh, that's correct. Yeah. Yeah.
So that's not polar molecule.
But if you can recognize that the molecule is not symmetrical, you can save all that and just say, this thing's polar. Oops. Because of its symmetry.
Polar.
If it is symmetrical, it's polar.
If it's not symmetrical. If it is symmetrical, it's like the table. They're pushing each other, they're canceling each other out, right? So if those are all fluorine bonds instead of 2 hydrogen bonds, it's going to be nonpolar because it's 100% symmetrical.
Non-polar.
There's no lone pairs. The lone pairs make it not symmetrical. And if that's just too much to remember, then just go with these steps and just follow it. And it works. Okay? Any others you want to try on here? What about CH2O? Without doing anything, what do you think? Polar or nonpolar?
It's polar
Polar.
because of.
That carbon-oxygen bond makes it a polar bond, and then you can see that it's not symmetrical without doing anything. Now, guys, I wouldn't just guess on these. Draw these, practice at doing it that way. But as you get good at this, you could just say, yeah, that's nonpolar. Yeah, that's polar. You could just look at it and say, once you get good at it. Let's get good at it first, okay? But some people get good faster than the others, right? Yeah.
I forget, would we put the C or the O as the central, if we were to draw that one out?
Yeah, what would you put the central atom? C, carbon or oxygen? Why carbon? Less electronegative.
Less electrons.
And let's think about this. Why does the least electronegative go in the center? Because there's electrons on the outside.
Yeah.
So it's going to be pulling that way, right? Does that make sense?
Yeah.
Okay. Yeah, Chad.
For the first one I would group for, with phosphate and bromine.
Uh-huh.
Is the phosphate or bromine
Let's be careful on our naming. Phosphorus.
phosphorus? Sorry.
Phosphate is PO43 minus. Just
Correct.
okay.
Apologize.
So what about it?
So which one would be the central? I mean, I think it's phosphorus, but which one is the center atom because they look?
Yeah, which one is less electronegative here? What? Phosphorus is less?
Yeah.
Then it doesn't go against our rule there.
But how do you determine that?
You look at the electronegativity chart and you look at the numbers.
Oh, this one, right.
Whatever one has a lower value. Thanks for asking. Are we good? Any other questions before we move on? We can take a break because that's kind of the middle of our topic today. We have one more topic and then, let's see, I think we're done.
We go home.
Unless you have another class. see. So, oh, yeah, we got a little bit, okay. Are we good? We have about 6 minutes before real break time. Do you guys want to take a break now? Good stopping point? Okay. Unless we had any other questions on, you want to do some more during break? If you want to try some of these, go for it. I have the answer key up here. You can come and check it out. Or it's online. Okay. All right, let's take a break. Uh-huh. Yeah, all the answer keys to these worksheets are online. If you can't find them, let me know and I'll help you navigate to it.